Fantastic. Hi, everyone. I am very excited to introduce Marinel Vasquez, who is one of my best friends. So this is very cool to have her here and talk to us about human-robot interaction. Mary, I call her Mary. Mary and I have done our grad school times together, and she's now a professor at Yale, and she is running a group that focuses on I guess per her title, multi-party HRI, but that basically means the understanding how groups of people interact with robots. And sort of when she talks about social navigation, she talks about, usually multiple robots with multiple humans actually doing stuff together. So I think this should be a really fun talk. She's one of the most creative people I know. She's also one of the kindest people I know. And so, listen to what she has to say and see if we have cool things that we might want to actually do together with her group. Take it away, Mary.
All right, thank you so much, Anka. It's great to be here. It's quite exciting to tell you about some of the stuff that we've been thinking about. And just to sort of set the stage for here, if I'm not looking this way, but I'm looking this way, is because you're all on my other screen. And so I apologize if that seems awkward, but this is the social person in me that has trained me to think about these things. So anyways, today I want to tell you about human-robot interaction, and in particular, I want to start by putting out this picture because I think this is the most prototypical image that you might get when you think about HRI, human-robot interaction, right? You think about robots helping users of all kinds, but perhaps the world doesn't look like this all the time, right? Maybe the world looks a little bit more like this. And so this realization, right, that is not just one user that perhaps a robot is trying to help or interact with, has brought a lot of interest into this field of multi-party HRI. Now, at a high level, I would describe the goals of this research field as twofold. I would say we want to understand how people perceive robots and interact with them so that we can, design the best robots we can for these interactions. And second, we want to build autonomy because, well, we want these robots to do things on their own. And so I've structured my talk today to basically talk about these two lines of research, which we work in my lab, and hopefully get you excited about multi-party HRI as a very rich field of study where there's, lots of open questions and interesting things to discover. Okay. And so let me start with part one. This is, more focused on sort of experimental side of things, how people perceive robots and interact with them. And I'll tell you the punchline right now, because this is, I'd say, message number one from this talk. Multi-party interactions are not necessarily a trivial generalization of one-on-one encounters. Okay. Now, to motivate sort of this idea, I want to tell you the story of how we got interested in robot abuse. And that was because this video came out and we were all like, unbelievable. This robot is being deployed in a mall. And what you see is many kids hitting it, punching it, kicking it, and doing all sorts of things to this robot. What's going on here, right? Now, it turns out that after this video came along, a lot of news talked about robot abuse as well. And we as roboticists, we got worried. What is happening? We don't want robots to be abused. This is, on the one hand, kind of risky. What if the robot gets damaged? What is it going to do after that? And well, second, if robots are being mistreated, they're not going to be able to help people the way we kind of actually envision. And all this work we're putting to making robots help people wouldn't actually materialize. And so what can robots do about this, right? Well, rule number one of robotics, we don't want robots to get back at people. So that's not an option. And so then we thought, well, robots are not alone, right? Maybe they can leverage their social context to mitigate abuse. Maybe they can induce human bystanders to intervene and help them out. Turns out this is actually not a new idea, right? This is something that is often taught to kids in elementary schools because it has been seen that this is a strategy that can help with anti-bullying. And it just, it's easy to implement. You can get someone to help you out. If that person can speak up, well, chances are things are going to be better. And so we said, let's try this out with a robot. What would happen? Now, of course, we had to induce robot abuse to test out, could we motivate a bystander to help a robot? And so what we did here was we set up a task where two people, a confederate and a participant, confederate being a member of our team that the participant didn't know was a member of our team, was pretending to be a participant. And so these two people were here trying to learn Braille, doing a memorization task on a tablet, and the confederate would fail at very specific times. And when that happened, it would sort of discharge its anger towards the poor robot on the table, okay? And so let me show you here an example. Hopefully you can hear, and if you cannot hear, let me know.
Oh, piece of shit.
And so the first, mistreatment was sort of verbal abuse, and that one escalating all the way to physical abuse. And so the idea was, right, could the robot do something by reacting in some way to these abuses to motivate the participant to intervene and say something to the confederate, like, hey, don't do that, And so we tried out different types of responses for the robot. In one case, it did nothing. In another case, it shut down for a couple of seconds. Let me show you. And then it came back up. And in another case, it first expressed sadness. And then eventually, after a couple of mistreatments, then it was angry. So I'll show you first sadness and then angry. All right. Now, what we found was that the shutdown response led to higher perceptions of the verbal abuse than the other ones, but there was no difference for physical abuse. There, we were basically maxing out what we could do to the robot at that point. Now, in terms of interventions, there was no difference between these different reactions. What happens was that most people righted the robot after it was flipped over, so at least they helped it on that. But 27 of 48 participants made some verbally discouraging comments, and out of those, only 2 directly intervened or questioned the action. So for instance, one person said, you shouldn't do that. And so, we were quite disappointed by this outcome. We thought that, come on, such a cute robot, how couldn't it motivate someone to say something? But this is a really hard problem, right? We don't like conflict. It's like a really hard thing to get someone to do. And so we looked around, and what happened afterwards was that we discovered that in human-robot interaction, there is evidence that sometimes conformity effects emerge in this type of social encounters. Conformity is a group effect where a person in a group might align with the majority of the group, even though they might not necessarily agree with whatever decision is we made or with their line of thought, but they do it because they want to be part of the group, okay? And so we thought, well, if this type of effect happens in HRI, could we use now some, group social influence to induce prosocial interventions from a bystander? What would happen if we now add more robots to our setup and those robots respond to the abuse to kind of show that, hey, this shouldn't be happening? Would then a human say something to the confederate? Let's see. So we decided to change the task to make sure that people all felt part of a group, because this is key to those type of conformity effects. And so now we had a participant and a confederate. This is the participant on the left, confederate on the right, build these different structures like a tree, a fort, and a pool. And as this was happening, there were 3 robots on the table, all of which were pointing at different pieces that should be used to sort of build the next structure. And so in a way, they were trying to help a little bit with the task. Now, one of these robots, the one that you see right here, it oftentimes made mistakes. And when that happened, then the confederate abused it, okay? Similar to the prior setup. Now, the test that we were checking was, would reactions by the other robots on the table induce the participant to intervene? Let me show you a reaction here. So that was pushing down the head after the abuse. And then the other robots start turning. And then express sadness towards the abused robot, okay? So this was our experimental condition. The control condition was the robots, the other robots on the table, these two did nothing. They just stayed still, okay? Now, what we found in this case was that there were more interventions in the experimental condition when the robots turn and express sadness. And not only more interventions, but more participants that intervene at least once. And so we thought, wow, this is amazing, right? Let me show you one example here of an intervention. And so the guy was like, whoa, 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 don't break it, don't break it, in case you couldn't hear. And so to me, right, this was really, you know, it blew my mind that we actually got this to work. But the mystery that still stands is, why exactly is this happening? So we designed this experiment with the thought that the robots turning around and expressing sadness would increase empathy on the participant towards the abused robot. That's what we thought. But we didn't find any strong evidence that the participants were feeling, you know, more empathy towards the robot in this condition versus the control condition. So it could have been that maybe we didn't measure the right thing, or maybe, here's an alternative hypothesis, maybe the control condition induced conformity to doing nothing. Could be. And so, you know, more research is needed to actually understand the fundamental psychological mechanism that is driving people to act. But nonetheless, going back to my first message, multi-party interactions are not necessarily a trivial generalization of one-on-one encounters. And one reason is because group effects can emerge in this type of interactions that you just wouldn't see in one-on-one encounters. And these effects may offer opportunities to do novel things from an HRI perspective. Now, in addition to this, there has also been research that has shown that very subtle robot behaviors, like the way in which a robot gazes towards people, can actually influence participation in these interactions. And even more importantly, there has also been research that's shown that robots can strengthen human bonds in this type of multi-party interactions. And so these are things that, you know, normally you wouldn't get to see on one-on-one settings because, well, there's no opportunity for these type of effects to emerge. And so I'm going to pause here for a second. I'm going to check any questions at this point before I move on.
I had a quick question.
Mm-hmm.
So you showed that you had this group of 2 robots. Did you happen to try a condition that was in between the control and your experimental condition where you only had one of the robots turn around and exert its like displeased noise and the other one didn't?
Yes. Mm-hmm. So we did not try that. That's actually a very great point, something that we could try in the future. One thing that I can tell you though is that group size has actually been correlated with conformity effects. Yeah. So, you know, actually the size of that group might actually influence what's going on. Another thing that we did not try, which is actually, I think, very important to try, is, well, what if the robot wasn't that cute? Like these really cute robots. I mean, I must say, right, in a way, we were using robots that were making our task relatively easy, right? Because it's very easy to see these expressions. It's very easy to sort of feel happy when the robot expresses happiness and so on, right? And so what would happen if we had different robots? We don't know. One thing we were trying also to think about is, you know, what other modifications to the behaviors we could do to sort of tease out, is it that it is conformity to no action, or is it conformity to the reaction of sadness? And so that's also something that, you know, we would need to follow up to sort of better understand. A great question.
Really
All right.
interesting. Thank you.
Yeah, no problem. Anything else at this point? All right. So I stopped here, right? Hopefully I got you excited about all sorts of interesting things that can happen in multi-party interactions. And I want to tell you sort of what to me is the big caveat of a lot of this work. And that is that for the most part, because these are very controlled studies, what you see here are very simple robot behaviors and perception, all based on scripted interactions, right? Based on what we expect to see happening, based on what we designed for this particular interaction scenario, right? And so that naturally brings me to part 2 of this talk, which is about autonomy. How can we advance, right, this level of autonomy for multi-party HRI? Now, at a very, very high level, I can think of solutions across one dimension where you might have on the one side model-based approaches and on the other side data-driven approaches. And note that when I say here model-based approaches, I don't mean having a dynamic sort transition function in an MDP. I mean actually describing what is happening in the multi-party interaction with a simple mathematical formula, perhaps drawing from psychology, right? And so for the talk today, I'm going to argue that there is very interesting solutions in this part of this space. These are what we call structured data-driven methods, where we're pushing on the data-driven side because there's just a lot of stuff going on in these interactions. And it seems hard to sort of describe everything with one formula. But we're not all the way in data-driven approaches because there's interesting structure in these problems that we should be thinking about exploiting, in my opinion. Okay. And so let me tell you sort of how I got to this part of this space. And in particular, I'll tell you this in relation to modeling spatial patterns of behavior, which is something that I've been doing now for quite a number of years. So when I started working on this, I was more on this side of this space. And the reason was the following. So we had created this furniture robot that you see here. This is work that I did in my PhD in collaboration with Disney Research. And we wanted this robot to engage children. And for that, you know, we had created this whole storyline. And the robot in the middle was going to give kids this souvenir, this piece of paper that you see them carrying in the picture. Now, after we gave them this piece of paper, very often the members of the conversation changed. And new conversation started right in front of a robot, even though we had planned all these other things for it to say to the children. They just didn't care. Okay. And so we thought, well, okay, how do we enable a robot to know who's conversing with whom, who's actually part of its group? Well, it turns out that whenever you converse with other people in open spaces, you stand in very repetitive ways, like, you know, face to face, in L-shaped formations, or maybe in circular formations. And this type of patterns that we call phase formations, or F formations in short, also turns out emerge in HRI. And we saw this in a number of experiments with our robot. And so we said, well, okay, if this happens, if there's actually a whole book that describes how these patterns emerge in social psychology, why don't we copy that and try to implement an algorithm that describes that mathematically, right? And so the way this book explains how these patterns happen is the following. Everybody has what is known as a transactional segment. This is just the space that extends forward from this person that includes whatever they're engaged with. And whenever you converse with other people, what you do is you naturally intersect your transactional segment with them, creating what is known as an O space for that phase formation. And so what most models for this type of interactions do, and what we did, was mathematically predict where an O space might be for a given person and check, ooh, in a scene, given that we know where everybody is, where are these O spaces intersecting? And if they're intersecting, aha, there's a group, okay? Now, turns out that if you have noisy sensors, you can use this type of model very well by adding a little bit of temporal consistency to predict who would be the members of a robot's group, or even detect other interactions nearby. Here's an example of an experiment with the furniture robot that I showed before, where the polygon that you see on the ground connects the people that are part of the robot's conversational group at that time. And what you'll see is that even though, skeletons sometimes even disappear and, tracking is very poor, nonetheless, that polygon on the ground actually stays relatively constant. So we could use this to actually study different orientation behaviors for the robot and different gaze behaviors for the robot based on sort of the state of the interaction. Now, when I was finishing my PhD, I thought, wow, this was great, right? We can actually run this thing all in a study with different numbers of people and so on. But I really couldn't see a way to add to my mathematical model all the many other things that actually matter for this type of formations. For instance, right, if you imagine having a robot in a museum, well, people may be standing side to side because they're talking to each other, but actually it turns out they're also part of a line because they're waiting to get to some part of the museum. And not only that, but sometimes actually people walk together, they're not just standing. And as they walk and they cross this line, they actually break apart from each other because they have to intersect other people and then they come back together. And well, if they enter an elevator, now the physical space matters a lot, right? Because people would naturally be fine being closer to one another because the space is very constrained. And so how do I add all these things that, matter because of the context of where that interaction is taking place to my very simple mathematical model? I just, I didn't see it. And so I thought, it seems like what we need are more flexible and generalizable approaches. We need to push right on the right side and see what we can do with data-driven methods. Now, at that point, I really was stuck because there were a couple of things that made multi-party interactions tricky. And so let me tell you some of them. So if I think about requirements for applying ML to this type of interactions, there are a couple of things that matter from a very practical perspective, okay? So one, you need to support a variable number of interactants. Two, ideally, you want models that accept unordered inputs. And three, we need models that allow us to reason about individual and interaction factors, potentially bottom up and top down reasoning all at the same time, maybe. Now, what I'm going to do is I'm going to walk you through each of these requirements, and then I'll tell you the story of how we got to where we're thinking about this model. So for these first two, let me first tell you about what is the most common approach to applying machine learning to these interactions. And that is very simple, right? I say I have these agents or actors or humans and robots. I have features for them, each of them, and I'm just going to concatenate them and pass them to my machine model and make a prediction. This seems pretty straightforward, right? Now, this is a very, very common approach. It has been used, for instance, to predict engagement at a group level. This is the work by Salam and colleagues. We have also used it in our own work to learn gaze policies for a robot in multi-party interactions. But of course, right, if suddenly a new person comes around, well, your model was only expecting a fixed number of features. What do you do now, right? It doesn't quite generalize that easily. And sometimes actually one very other common thing to do is that people say, oh, say for instance, in our work down here, this person was playing a game with this person. This is the left player. This is the right player relative to the robot. I'm going to make this first set of features, the features for the left player, okay? And then the second set of features, the features for the right player. Now, in this setup, there's actually different characteristics for people. One person in this experiment was actually a native English speaker. The other one was a person that was learning English, okay? And they could actually sit left or right, depending on the experiment condition. And so we might actually get bias depending on how many times the speaker sat on one side. And if then we go and test on a different situation where the speaker is sitting on the other side, oh, the model might not do as well because of that left and right, sort of arrangement. And so what did we do? Well, we did a data augmentation, right? Let's swap out in our data set who's the left player versus the right player. And that way, now the bias sort of disappears. Now, you may be able to get away with this like we did in this work, but I would argue it would be great if the machine learning model was actually permutation invariant to the order in which you pass the features for each of your agents, right? So it wouldn't necessarily need to matter, oh, this is always the first one versus this is the second one versus this is the third one. If I permute them, I would want to get sort of the same prediction, okay? Now, this last point here is about the need to model individual and interaction factors. And to justify this, I wanted to show you this framework that recently came out in this review of robots in groups and teams. So this is a framework that describes how you may want to think about of group interaction processes. On the sort of input side here, you have many things that matter. You have individual level factors for humans, for robots. You have group level factors like group composition and size, like we talked about before. And you might also have environmental level factors that matter. Now, all of these different things might change how your interaction process evolves. And this can be, human to robot interaction or human to human interaction. And out of this process, you might want different outcomes, maybe some sort of task performance, or maybe something about the way people are perceiving the group or the robot, and so on, right? Now, if you pay attention to this diagram, it's quite fascinating, everything that is said in here, because a lot of these things are not necessarily directly observable, even in the input space, okay? So for instance, you might have human skills, which maybe a robot may need to estimate based on interactions. You might have group level factors like type of group type in relation to, say, intimacy. Maybe these are things that also need to be estimated. And in the middle here, you actually have relational factors that you may need to estimate, right? So if you think about, say, human to human interaction or human robot interaction, one common relational factor that matters is attention. But how do you get attention? You might estimate it from gaze or head orientation or other raw features that are not necessarily attention as a whole. Attention is something that you have to estimate. And similarly, right, with sort of the other outcomes on this side, there are things that you may need to estimate that are not directly observable. And so what does this tell me, right? When you think about HRI in multi-party settings, you care about perhaps predicting individual factors, perhaps predicting relationship factors, and perhaps predicting factors over the whole group. And so I want models that can do all of these different things in a seamless way. Yeah, does that make sense? All right. And so getting back to sort of the idea of these structured models, what should be the type model that we should be thinking about here? Well, the first thing that occurred to us because of this need for permutation invariance was using deep set architectures. Now, I don't know if you're all familiar with deep sets, so I'll give you the gist here. This is an idea that actually I learned about it from work in point cloud processing, but more generally, you can apply it to any kind of mathematical set. So let's say that you have 3 elements, okay? These dots that I have here on the right, each of them may correspond to, say, the agents in my interaction, okay? And for each of them, I'm gonna have a feature. Well, what a deep set architecture would do is it would project that feature into a higher dimensional space and then compress it down into a fixed size representation using a symmetric mathematical operation. This is an operation that is permutation invariant, like averaging, like maximum, and so on. And so I'm going to apply this operation along the rows, and that's now going to give me a hopefully permutation invariant representation, right? Because that operation is symmetric. Yeah. I see confused face. Any questions about this? Hopefully this makes a lot of sense. It's very simple, right? Imagine you just apply max pooling across the rows, then no matter in which order you pass these input features on the left, you end up getting the same representation on the right. Yeah. All right. So we apply this to the problem of group detection under a framework that we thought of as graph clustering. Okay. And so how does this work? So imagine that I have a social scene with a number of people and their features. I can represent it as a graph. And if I can compute an edge weight that tells me how likely is it that those 2 nodes connected to that edge are part of the same group, then I can build an affinity matrix from which I can apply graph clustering and partition my graph into groups. Okay. Now, the key here to make this work is computing these weights, and that's where machine learning kicks in. And so we implement this as a network where the one side of the network, one stream, is going to compute a feature representation for the features for the two people connected to that edge. We call that the dyad transform. And then the other side is going to compute a contextual representation for everybody else that are nearby. And the way this is going to happen is exactly with that same deep set architecture that I mentioned before. We're going to get the features for everybody else in the graph, project them to a higher dimensional space, apply my symmetric operation, and then get a permutation invariant representation. And then we get those two representations, and from there compute our weight using just a standard multi-layer perceptron. Okay. Note that here we're using this deep set architecture to basically summarize whatever information is given by other people nearby the two people of interest. Now, if you add this context, turns out you can do better quantitatively in existing sort of benchmarks for group detection, where here higher is better. And this is a group detection score that basically penalizes you for having any wrong member in your group or missing anybody in your group. Now, let me show you sort of a fun video. So we tested this out on a robot in my lab. Here we were detecting people with a Kinect on top of the robot. And what you can see here is on the left side, the view from the Kinect. This is the view of the robot, which is moving a lot. And then down here, you can see a top-down view of the environment. Note that the agents are colored based on the groups that they're estimated to be part of. So these two people are said to be part of the same group right now. And the robot has a super tiny arrow that is also colored, which tells you which group the robot is part of. The red lines that you see there, they're actually telling you sort of the strength of that affinity value that we computed with a neural network. Now, there is no temporal consistency here. This is a frame by frame prediction. And yet the results are actually super consistent, which was kind of great for this type of application. All right. Now, here comes the twist. So after we had done this work, we realized that deep set architectures are actually a instantiation of a more powerful class of models called message passing graph neural networks. And we thought, well, what if we use those kinds of models? Now, the key thing here that I want to point out is that we actually really liked this graph representation at this point, because the graph was encoding information about individuals. It was allowing us to encode information about relationships, and we could use it to think about whole groups, just like I showed you before. And so we said, well, let's try to apply these message passing graph neural networks. Now, again, I don't know how many of you are familiar with these models. So if someone is not familiar, all right. So let me quickly explain how they work. So these models, what they do is they would transform a graph into another graph. So let me first define a graph. I'm going to say a graph is a collection of features where I have global attributes that help me contextualize that graph. In our case, I'll show you an example where these global attributes are, for instance, environmental information. Then we also have a set of nodes, and each of the nodes have features. And then we also have edge attributes along with each edge, where here I'm drawing this graph as if it was directed, but you can very easily extend this to an undirected graph by just adding edges in both directions and replicating the features, okay? And so these GNNs, they will transform a graph into a new set of graph by updating all of these features. And this is gonna happen in 3 steps. First, we're gonna propagate information from nodes into edges. And so we're gonna have a differentiable function phi that is gonna take my prior edge feature, the features for the nodes connected to that edge, and my global graph attribute, and compute what a new edge would be. And this is done for all of the edges in the graph. Then I'm going to propagate information from the edges into the nodes. And for that, I'm going to first aggregate information over all of my edges that end in a node. And this is where the connection starts happening with deep sets, because this aggregation operation is oftentimes implemented via symmetric operation, such that the topology of that graph doesn't matter. You can still apply the same procedure. And then once you've aggregated this information into a feature vector, then you can update your node with that aggregated information, your past node feature, and your global graph attribute. And then lastly, you can update your global graph attribute by doing a similar procedure: aggregate over edges, aggregate over nodes, take your past global attribute and compute your new global attribute, okay? And so that's basically how GNNs work. You can stack them just like you can stack recurrent neural networks. And so we tried this out again, same problem, but now we change our prior model with this GNN. And here we supervise the model on a cross entropy loss on the edges based on ground truth groups that we knew of in a data set. Now, what we found in the data set that for which I showed you results before is that this model really performed similarly to the prior one that we had. However, when we tried this out in a more complicated data set, like this one that you see here, what we found was that as we had more features for the nodes, then the GNN actually improved in performance, whereas our other model actually saturated. And the main message I want to give you here is that, to me, this is happening because the GNN is fully taking advantage of the structure of that graph, whereas our prior model was kind of an approximation of how to take advantage of that structure, where we're kind of hacking how we were reasoning about edges. And because the GNN is actually thinking about edges in relationship to people and propagating that information more effectively, to me, that's really why you see this sort of results coming up. Now, there's still a lot to be done here, right? This performance is not quite great, especially for this type of scenes. And I think part of that is because, at least for this data set, we actually don't have exact people orientation. We were estimating it out of visual features. And I think the visual features we were using were actually not that great. But nonetheless, the main point I want to make is actually our prior model didn't do that great. It's actually the GNN, the one that is performing better here. And so I've shown you, right, an example where these GNNs can be used to reason about interpersonal factors, which is, who's interacting with whom. I want to quickly give you another example where they're being used to reason about group level factors. And so now I'm going to slightly change the problem, okay? I'm going to say, given that I know that there's a couple of people in a group, like these ones that you see here with the orange arrows, and given a map of the environment, like this sort of gray area with occupancy information, I want to predict where a robot should be placed to sort of be part of that conversational group, okay? And so when we started working on this problem, we said, do we really need machine learning for this? If you already know who's part of the group, these groups are oftentimes very circular. Why don't we just take advantage of that and make our life easier, right? And so we tried to do that. Well, what if we, take those people, feed a circular shape to them, compute sort of empty space for the robot along that circular shape using optimization. And so here, for instance, we set up our loss as a combination of being away from the circle, where darker is higher cost, not being too close to people, these blobs are just violations to personal space, and then not being in occupied parts of the region. Yeah. And then you can throw this to your favorite optimizer and get a position for your robot. And then you can say, well, let's just start. If we point the person towards the middle of the group, it should be good enough, right? And so now, key to this procedure is that the optimization approach I showed you before is prone to local minima. So why don't we start from different initial locations and then get a distribution of potential poses for a robot, and then choose one that is likely, say, by looking for the mode of the distribution. And so that's actually what we tried right here. And what you can see, the orange arrows are people's position for the existing group, and then light purple are poses predicted by this method, and dark purple is the one that comes out as finally the one solution. Now, this actually worked really good for many, many cases, but I'll show you the example that got me really annoyed, and that is if people are roughly collinear. Then defining a circle is not quite that trivial, right? And so we said, okay, fine, let's see what happens if we actually use machine learning on this problem. Now, this is a generative problem, so we went for a generative adversarial network, and we set it up such that the input to the generator and the discriminator, in this case a critic, is actually that graph with information in the nodes about the people that are part of the group. And then my global graph attribute would be this occupancy map for the environment. And in the case of the generator, I'm also going to pass there the latent sort of vector that produces different outputs for poses for the robot. Now, the critic is very similar. The main difference is that as input, you're also going to get the pose that is output from the generator, or is actually coming from your ground truth data set. And because this is a Wasserstein GAN, we're not necessarily classifying this information. We're actually outputting a feature that we hope to make different between the distribution of true groups and the distribution of sort of generated poses for input groups. And so the key thing I want to highlight in this setup is how these two networks are set up. And that is that there are two processing streams. One is a GNN that reasons about the orientation and positioning of people in the group. This is very similar to the deep set architecture that I showed you before. And then another one is a GNN that reasons about people's position in relation to the occupancy map that we have of the ground. And having those two actually was really important to making this work. If you want more details, just ask me at the end, and I'm happy to show you, exactly how we implemented this. Now, we're not talking about GANs, so we need actually a lot more data than what we can get from existing data sets for this type of problem. And so we went to simulation and we took environments of realistic, human worlds from the iGibson environment. We created environment layouts, and then we made very simple circular groups in free space. Now, these groups are not super realistic, so we did a little bit of data augmentation to warp these groups and add some noise to the people's angular position to kind of make things a little bit more similar to what you might actually see in a real world data set. And so just to show you some examples here, what you have here on the left are outputs from the geometric approach that I described first. The star means that we're computing a distribution of poses. And then on the right, you have outputs from the GAN. And overall, I would say they both perform pretty well. Now, one key difference is that the GAN tends to output a more sort of compact distribution than the geometric approach. But in terms of quantitative metrics that we compute, overall, they did well. And so we kept wondering, well, which one is better? How do we tell? And we said, well, how about we ask people? And so we decided to run an online study where we rendered our robot according to each of these methods in a 3D world that looked like an existing data set of group formations. And then we said, hey, do you think that this robot is actually positioned to be part of the group with the other people using a number of different statements? And what we found was actually quite interesting. So for group sizes of 4, 5, and 6 people, turns out that the GAN did better. Here, higher means more in line with the group. But for group sizes of 2 and 3, it turns out that the geometric approach did better. So what happened here? Well, we went back to the data, and what we realized was that oftentimes for small group sizes, the GAN would place the robot farther away from what the geometric approach would do. And this brings me to this very important, perhaps obvious at times, requirement for applying ML to multi-party HRI. And that is that, well, we need good data, right? So what happened before was that the data that we simulated, we just assumed that groups had always the same sort of circular shape, right? The radius of that circle was always the same, no matter how many people we had in the group. But if you have fewer people, it turns out people can stand a little bit closer together. You have more people, the group needs more space to all fit within that circle. And we didn't sort of account for that in your simulated data, therefore we got the results that we got. Now, the fact that we need good data is probably obvious to you at this point, given all of the work that has been happening in ML over the last years. What I think is not so obvious is how do we create good data in a scalable manner for multi-party HRI? Now, we've been thinking a little bit about this over the last year, especially with COVID. And I'll tell you sort of what we're thinking of in these lines. So one idea is obviously, let's take advantage of the data sets of human-human interactions that already exist. We've done this in the work that I just shown you, and to some extent, it can work in certain applications. However, the caveat is that we don't know if people will react to robots in the same way that we react to people in those data sets, right? And so if that's a problem, this seems like a very bad option. Now, the other option here is that you just go into the real world and get data in the real world by deploying your robot, if possible, outside of the lab for as long as you can. And this is actually something that we're trying to do now. This is a cart that we built in my lab, where literally all of the compute and everything that you need to run the robot on the top is at the bottom of the cart. And the cart is made exactly the size that you need, so we can put it in the elevator and take it to buildings that are connected to our own building and just, find power, deploy it, and run an experiment right there. Now, I can tell you it has taken us a long time to get to the point where we can actually deploy this cart. So there's a lot of engineering effort that has to happen to make this work. And so we've been thinking, well, maybe there's sort of a middle ground now, especially given the amazing simulation technologies that we have out of the gaming industry and sort of cloud compute tools that we have at our disposal. And so one thing that maybe we can do is embed the simulations in regular browsers and allow people to interact with these robots via the simulations. Now, obviously, this wouldn't work for all HRI applications, but perhaps for some applications like navigation, which is what we've been using here, maybe this is a way to scale data collection and do rapid prototyping. And so how are we doing this? By the way, all of these things that I'm going to talk about now are open source. So if you're interested in testing them out, let me know, and I can definitely point you in the right direction. So the first thing we did was actually build tools to study social navigation in Unity, because Unity is a game engine that actually has a lot of easy tools to allow you to create worlds, and there's lots of assets that you can easily sort of put into your simulations and so on. Now, we wanted to build a simulation that we could easily use to transfer to the real world, or at least as easily as possible. And so we made sure to integrate our tools with the robot operating system such that all the code that is running on a simulated robot is actually running within ROS and then just being rendered on that simulation for the purposes of making things fast. Now, once we had this simulation environment, we built infrastructure to serve the simulation on a regular web browser. What this means is that people in their browser can access this simulation and they don't need to install anything. They don't need a fancy GPU to run it. Everything is being rendered on the cloud. Now, how does this work? Well, what we do is we take this simulation, all of the ROS dependencies, everything that you need, encapsulate it into a Docker image, and include in there a graphical desktop sharing server that allows us to stream the GUI via the web, and also take back the sort of input from the person back into the simulation. And so with that, what we can do is define navigation tasks, use that to create our simulations on the cloud, embed that simulation on a browser, and then just allow people via a crowdsourcing tool to access all of these many surveys and collect data in parallel for all of them via this system. Now, I don't have time to tell you more low-level details, but I'll show you at least a video so that you get an idea of how this works. So this is one of the simulations of sort of my lab, actually, where we're embedding it into a browser and we're giving access to a person to control a human avatar with their keyboard. Now, as they're doing this, there's a robot in the environment. That robot is controlled in the back end on the cloud via ROS. And now we can tell people, hey, as you were completing this task, navigating to this place, what do you think, for instance, of the motion of this robot nearby you? Or can you follow the robot to a given destination? And so on and so forth. And then, because this is all a survey, once they finish the simulation, we can ask them questions as part of the survey to get their feedback about what their experience was like and do kind of a more typical HRI study as part of this online experience. Now, I can tell you that the feedback that we collect from these interactive surveys can differ from feedback that we collect from video surveys, because we've done an experiment to get that data. However, we don't know yet which of these two sets of feedbacks is closer to the real world. And that's something that we're actually planning on running a study on in the spring. And so I can report back once we have more data. Now, my impression so far is that being in the simulation is a totally different experience than actually watching a robot interacting with a person in a video. And so I suspect that the interactive simulation will be closer to the real world, However, there are important challenges, especially in terms of how people provide input to, say, control their character, which can pose limitations as to how realistic this data might be at the end of the day. Now, the other thing we're doing here is, because now we have different worlds that we have simulated and ways to render sort of these worlds in dynamic ways, we're testing different ways to adapt navigation policies to different social contexts. And we're also working on a benchmark, which hopefully will come out next spring. And so if you're working in social navigation, please keep an eye on this, as we're very curious to see, how different algorithms might do in this kind of setup. Now, I'm going to wrap up this talk, and I'm going to summarize sort of the key ideas of this second part. So I've argued today for structured data-driven methods. In particular, I've argued for representing group interactions via graphs. And you should know that this is actually not a new idea on itself. This idea is inspired by social network analysis that has been representing interactions like graphs for a while. I would say the very big difference that you want to take into consideration when you use graph for situated interactions is that in social networks, normally these graphs are really big. And you're thinking about generalization with respect to a chunk of the graph that you didn't see at training time. In situated group interactions, these graphs are rather small. There's only so many people that can interact with a robot at a time. However, these graphs change at a way faster pace, and generalization typically is with respect to new groups that you need to deal with. And so that, obviously entails some differences in terms of how you measure performance and how you reason about these graphs in practice. Now, I've also told you that perhaps a good way to reason about these graphs is using message passing graph neural networks. And the algorithm that I described to you is actually inspired by belief propagation in graphical models. And so there's a lot of similarities in terms of how information is propagating from nodes to edges and so on. The key difference, though, right, if you were to apply graphical models to this type of problems, is that neural networks can learn representations from data. And I think there's a lot of opportunities for that in HRI. Now, I show you two examples of using GNNs to reason about interpersonal factors and group level factors, but there are lots of open questions, which I'm happy to talk about, like how do you deal with uncertainty? How do you deal with causality? I think these are very big questions that you should all be thinking about, hopefully. And I want to end by thanking all of the many students that made this possible and our collaborators and sort of all of our funding sources. And by the way, Yale is hiring in AI. So if you're a PhD that is close to finishing, consider Yale as a potential place to continue your career. And so I'll leave you here the link to my lab website, and I'm happy to take more questions.
Thank you so much.